Yo, dude, what's up? It's been a while. Hey, yeah, I've been good. How about you? How's the family? How's the kids? Yeah, they're doing great, thanks. Say, how's the weather over there? The weather? It's pretty nice outside actually right now. Clear skies, a little bit of clouds. Really? It's the same over here. What a coincidence. Wait. Teacher Brandon here. Just for the record, real-time systems, real-time programming, and real-time applications are used interchangeably throughout this report. Enjoy! Real-time programs are the ones that need to execute their code within a certain time frame. Obviously, this is a very vague statement, and it can apply to numerous amounts of systems and applications that we interact with daily. From video and audio calling to online shopping, gaming, and even instant messaging, all of these use real-time systems. But to understand how these systems work, you must first dive into the four main computer science concepts behind them. The first is the idea of interrupts. This is the idea that a CPU's task can be cancelled at any moment when it receives the interrupt signal. Whereas a signal can be received from a lot of different places, but usually they come from something called preemption, or rather a preemptive task. These are high priority tasks that need to get done now. Bro, mom needs you to take out the trash right now. Right now, or... So when one of these tasks arise, the CPU drops whatever it's doing and finishes the preemptive task first. Okay, I'll do it right now. I'm coming. Once the preemptive task is finished, the CPU will return to whatever it was doing before, thanks to a concept called task context, or a routine called the interrupt service routine. Before a preemptive task is run, this routine will run and save the state of the CPU, and once the preemptive task is done, it will restore that state to the CPU. Man. What was I doing again? Filing your nails. This is the same way us humans perceive to multitask. We aren't actually thinking about multiple things at once, rather we are quickly changing contexts in our brain. Finally, there is the concept of task scheduling. All tasks are split into two queues. There is background tasks and foreground tasks. High priority tasks are put into the foreground group, and low priority tasks are put into the background group. Foreground tasks are run as soon as they are queued, and new tasks are put into the queue based on the designated priority number they are given. Yo dude, don't you have a comp sci report or something you should do tonight? Yeah, look at all that, yeah. Dinner's ready, come down now. Man, background tasks can only run when there are no foreground tasks running. These two are sorted based on a designated priority number. Man, oh man, am I full. That was a good dinner. Bro, you're on dishes duty today. Yeah, I'll do that after my report. Now that we understand these concepts, we can move on to the three models of real-time programming. These are the synchronous model, the scheduled model, and the timed model. In the synchronous model, all tasks and computations are run instantaneously. As soon as an input is received, the task is run and outputted. Yo dude, what's 4 plus 4? 8. 8 squared? 64. Okay, and what's the quadratic formula? Negative b plus or minus the square root of... In the scheduled model, all tasks are sorted into a queue based on the task scheduler, who determines what the priority of each task is. This model heavily relies on the concepts of foreground and background tasks. B squared minus 4ac over 2a. Nice! And by the way, don't forget to do your laundry. It's kind of piling up in here. Yo, do you guys smell something burning as well? My pizza! Finally, we have the timed model, where the programmer decides exactly how much time a task will take. The output will only be accepted if the timer does not run out before a task is finished. If the task finishes early, it will wait until the end of the timer before it outputs its results. Man, I think I set the timer for too long. Now that you know how real-time systems work and the different models for programming one of these, we can start to classify these systems into 3 distinct groups based on the possible consequences for a missed deadline. These are the hard real-time system, the firm real-time system, and the soft real-time system. In the hard real-time system, missing a deadline will have catastrophic and irreversible damage and possible failure of the entire system. This includes things like property damage, monetary loss, and even death in some cases. So deadlines in hard real-time systems cannot be missed under any circumstances whatsoever. Who farted? It smells like rotten eggs in here. Don't look at me, I've been on an empty stomach the whole day. My farts are loud, y'all would have heard it. In firm real-time systems, the deadline won't cause someone to die, but it will make the output useless. These are systems like assembly lines, wherein if a part is put in out of order, the rest of the product is useless. It doesn't work anymore, and they will have to be scrapped, thereby wasting all the time spent making that product. Yo, Brandon! I was supposed to put the clothes in the dryer and then the washing machine, right? No, it's the other way around, genius. Man! Have fun doing that again. In soft real-time systems, missing a deadline is perfectly fine, but the more time that passes, the less useful the output will be. These are scenarios like multiplayer games where a packet can get lost or frames drop. Oh, that was lag, guys. Yeah, sorry, that was lag. My Wi-Fi is acting up, I don't know what's happening. There are also minor classifications that can be applied to these systems. There's the clock-based system, wherein operations happen at a specific interval or time of the day. There are event-based systems, where operations happen in response to another action. Now, put those two in a room and boom bam, their baby is the interactive system, wherein it is started off with a reactionary system with an event, but they must run within a given time constraint on the clock. If real-time systems are so powerful, then what are their current applications today? Well, I'm glad you asked. Hey Google, turn off my light. Hey Google, turn on my light. Okay, but seriously, from smart home devices to video games, instant messaging, and even spaceships, real-time applications ensure that in this new digital age, everything happens in the now. And real-time systems will only continue to advance as AI and machine learning seep into every aspect of our lives. Real-time systems help these machines sift through copious amounts of data that is generated every day so we can lead more efficient and well-informed lives. And its impact on society can already be seen in our day-to-day lives. Up-to-the-minute news updates, tweets causing political divide, and 5-year-olds on their iPads at restaurants. And that's the rundown on real-time programming, presented to you by Brandon. And Brandon! Don't forget Brandon! Someone call my name?